Hi everyone, this is a quick lecture on lecture A29, which is the hypothesis testing for correlation coefficient and the regression model. So the outline of the lecture is very quick. There are just two hypothesis tests. The one is for a Pearson correlation coefficient and the second one is for a Spearman's rank correlation coefficient. So for the Pearson correlation coefficient, we use the sample estimate, which is R, and that estimates the population correlation coefficient rho. So that looks like a P, but it's pronounced as rho, R-H-O. In order to perform the hypothesis testing using the following steps of the hypothesis test, we have the hypothesis, and under the null hypothesis, we're saying that this correlation coefficient is equal to 0 versus that it's not equal to 0, and we specify a level of significance alpha. Then we have the rejection criterion. We reject H0 if our test statistics, which we will calculate, R must be greater than R degrees of freedom alpha, and we get this value here from the tables in your books, and that is from the ordinary coefficient table, and your degrees of freedom is n-2. Then the test statistic, and we calculate that R as our test statistic, and it's in the calculation of the Pearson correlation coefficient that you guys did in the second block. But the formula will be given to you. Then we make our decision based on step 2, whether to reject or fail to reject H0, and make our conclusion based on it. So looking at the first example in your notes, we have a group of strawberry plants that were grown in pots in a greenhouse, and measurements were taken on Y, the crop yield, and X, the corresponding level of nitrogen present in the leaf at the time of the picking. So we want to test whether the Pearson correlation coefficient is significantly different from 0 at these different significance levels. And we have the data as follows. So we have 20 values of X and 20 values of Y. The first step is then to state the hypothesis. So we have under H0 that rho is equal to 0 versus H1 where rho is not equal to 0. So that's pronounced as rho, R-H-O. And remember that signifies the population. R is the sample estimate. Then we have alpha. We want to test for at a 0.1%, at a 1%, and at a 5% significance level. Note that even though it's a two-sided, we are not going to divide alpha by 2. So then we have a second step as reject H0 if R is greater than R degrees of freedom at alpha, and remember the degrees of freedom is n-2, so we're going to look at 18 because there are 20 of them. So looking at these values in your table, and in your notes, there's a section in your notes with statistical tables, and I think it's called table 33.5. You'll find that ordinary coefficient table. So we're going to have for R 18 at 0.1% to be 0.679, and R18 at the 1% significance level will be 0.561, and the last one, R18 at 5% significance level, equals to 0.441. Okay, and there we've got our critical values for those three different significance levels. Then the third step is to calculate the test statistic. So if you remember the formula which you guys did in the second block, you need to calculate R. Sometimes there's an X and Y at the bottom over there, but we'll just keep it as that. It's the sum of squares of X and Y divided by the square root of S XX and times the square root of the sum of squares of the y. And if we remember this formula over here, we have the sum of xi yi minus 1 over n sum of xi sum of yi divided by the square root of the sum of squares xs, which is the sum of xi squared minus 1 over n sum of xi all squared, and we want the square root of that multiplied by the sum of yi's squared minus 1 over n sum of yi all squared. Okay, so we're going to find these values obviously in the calculator using the data. So the sum of xi yi, the sum of xi, sum of yi, sum of xi squared, sum of yi squared. So we're going to find all these values in your calculator using the mode function table to find those values. And those values are, once we have all those values, we can plug those values into this formula over here. So r will be 0.5698, and that is my test statistic. Then the decision we make given our test statistic of 0.5698 and our different various values of the critical value, we had 0.679 at the 1%, we had at the 0.1%, we had 0.561 at the 1% and 0.444 at the 5%. So over here, this one is greater, and then we have again 5698, 0.5698, and we have greater there, and we have greater there. So over there, we're going to fail to reject. Remember, this is at 0.1%, and here we're going to reject the null hypothesis at the 1% and reject there as well at the 5% significance level. Okay, then our conclusion will be that because we failed to reject at the 0.1%, we can say, given our null hypothesis, that the null hypothesis stating that the correlation coefficient is equal to 0, then when we fail to reject that, we're saying that the rho is not different from 0. Here we're saying that rho is different from 0, and over here as well, rho is different from 0. So there is then a correlation between x and y. So there's a nice conclusion in your notes, and let's talk about the correlation between y and x is not significantly different from 0 at the 0.1% significance level. That is, they are not related. But at the 5% and the 1% significance level, the correlation between y and x is significantly different from 0. That is, that they are related. So that's a nice conclusion to the correlation coefficient between x and y. So something to note, although statistically we can infer if two variables are correlated or not, we cannot conclude there's a cause and effect relationship from this. And the Pearson correlation coefficient R, remember R is the sample one, measures a linear relationship, and it's best used when at least one of x and y is normal or normally distributed. Otherwise we have a non-parametric analog. And then remember, you might have outliers in your data, and they distort the correlation coefficient, and these outliers can be easily detected by a scatter diagram. Thus, if outliers exist, there's no use of finding R. If there's a significant linear correlation between two variables, then one of the 5 situations can be true. There's a direct cause and effect relationship, or there's a reverse cause and effect relationship. The relationship may be caused by a third variable. The relationship may be caused by a complex interaction of several variables, or the relationship just could be coincidental. Then we come to the hypothesis testing for the Spearman rank correlation coefficient, and the same procedure as in the correlation testing, except that one has to be very careful when using the tables. So there'll be different rules depending on the sample size, which table to look at. So we have the hypothesis. Now we don't look at row, we look at the row of S, because it's now the rank correlation coefficient, and under the null hypothesis it's equal to 0, under the alternative it's not equal to 0. Then we reject H0 if RS, so this is going to be a different formula, is greater than my critical value, but my critical value will depend on the sample size. So if n is less than or equal to 10, we use the special table which is called the Spearman's rank correlation coefficient table, and you'll find that at the bottom of that ordinary correlation coefficient table in your notes. And if n is greater than 10, we could use the ordinary correlation coefficient table, so that first table, or we can use a t-table using that formula there, and we say that that's distributed with n minus 2 in the t-table with alpha as my significance level. So either one you could use. Then we have our test statistic. So we decide which variable is x and y, and usually that is given in the question. We rank these x and y observations independently of each other in ascending order. And then we find the difference between each rank of x and y, between the x and y pair, and then we calculate the RS. So basically you're going to take your data, you're going to rank the data independently, x and y independently, and then those ranks you're going to find the differences and then calculate RS, and then we label the differences as DI. So DRS will be the 1 minus 6 times the sum of those differences squared divided by n into n squared minus 1. And you'll see how we'll do this in an example after this. So the decision then obviously is based on the step 2, whether to reject or fail to reject H0, and we make our conclusion. So here we have an example, and the data here is already ranked. So we have group 1, it's ranked, you can see it's this one is the first value, this one's the second, this one's the third, and so on, and in total we have 8 values. This group 2 is ranked independently of group 1, so the actual data values are not in this table. It's because the data is given has been ranked already, so you won't have to do that. But there is a question in your tutorials, tutorial 16, question 2, the data is not ranked, so you will have to rank that x and that y first before you find the differences. So let's have a look at this question over here. So we want to test, we want to do the hypothesis test on the Spearman rank correlation coefficient. So here we have example 2, and the hypothesis is now on the Spearman's rank correlation coefficient. So under H0, it's going to be rho S is equal to 0 versus H1, where rho S is not equal to 0, and we have alpha as 0.05, and we have 0.01. So we have 5% and 1%, and our rejection criterion is reject H0 if, remember, the test statistic RS is greater than R degrees of freedom at alpha. Now remember, n was less than 10. So go back to the example. We have 1, 2, 3, 4, 5, 6, 7, 8. N was less than 10. So we're going to use the Spearman coefficient table because of that. I noticed that there's an error in your notes. It should be these values over there. Those values in your notes look at degrees of freedom as 8 and not 6. Then we have the test statistic. Now remember, the test statistic, we need to find those differences first because of that formula over there. So drawing that table with the with the ranks and then doing the differences from there. So the table is and then we have the rankings. So now we need to find the differences. So we'll take group 1 minus group 2, and that will give me 0, minus 1, 2 minus 1 is 1, 1, 2, minus 3, 2, and minus 2. And then remember, we need to take the square of that because in the formula it's asking for the sum of squares. So that will be 0, 1, 1, 1, 4, 9, 4, 4. And then remember, the formula is 1 minus 6 times the squares of the differences divided by n into n squared minus 1, and you'll find that this will equal to 1 minus 6. The sum of these will give me 24 divided by n is 8 and n squared is 64 minus 1, and this will give me a value of 0,714, and that is my test statistic. The fourth step is then the decision. So we had our test statistic as 0,714, and at the 5% significance level we had 0,886, so that one is less, so we're going to fail to reject at the 5%, and at the 1% we had 1, and again we're going to fail to reject. So again, fail to reject at 1%. At 1%. Okay, and then our conclusion, because we failed to reject H0, we are saying that there is no relation between the ranking of group 1 and group 2 at both the 1% at the 5% significance level. So to write that out, we say there is no relation between ranking of group 1 and group 2 at both the 5% and 1% level of significance. And that is the end of lecture A29. Before we end off, in your tutorial 16 there is a question that you could do, question 2, which is practice on the Spearman's rank correlation coefficient. Just a hint, you need to rank X and you need to rank Y. These are the actual values of X and Y. You need to rank them first before you find those differences. And then just to correct what's written over here, it should not be R is equal to 0. It should be row S is equal to 0, and then row S is not equal to 0. So just fix that in your notes. And as regarding question C, you don't need to do to construct a 95% confidence interval. Please email me if you have any questions. Thank you.